Welcome to Building Janky Programs. I'm Philip Forkner, professor at Pierce College. And also with us is Jasper Newkirk, is a student in the computer science department at the University of Washington in Tacoma. He's the BMOC. What's up?
What's up?
All right. So today we're gonna just do a quick one, I think, on recursion. And I think Jasper, you're gonna take the lead on this one, right? Maybe
Sure.
Do a share screen or something. Okay, cool. All right, so let's talk a little bit about a recursion. We started talking about it in class already, and so this is just going to be kind of a little additional bit to it. So, all right, so Jasper, I think you're going to talk natural numbers.
Yeah. All right. So natural numbers we can think of as summations, right? So the summation of, what is it? N to X or X to N, something like that.
So we're going to add up like 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc. Yeah. Add up all the numbers.
So we can think of it as 1 plus 2 plus 3 plus 4 plus 5 because addition's cool, right? We can do the other way, which is also fine. We can do it iteratively using a for loop, right? So we can have a for int I equals 0 or 1, I guess. It doesn't have to be 0. While I is less than 6, I plus plus, and then we can just have some int sum, which is, oh man, I probably should have had an int sum already, shouldn't I have? Okay. Yeah,
probably. Yeah, I
now.
think so. I think so. Yeah, because you got to start off with you got to start off with
Okay, so we have an int sum equals 0, and then we can have a for loop and say sum plus equals I, and then now sum should be 15. So that's how we can do it iteratively. We can do it mathematically. So 5 times 6 divided by 2.
with a semicolon. Yeah.
No. I don't have a multiplication sign. Yeah, so 5 times 6 divided by 2 is 15. You can think of it as n times n plus 1 divided by 2 is equal to the summation, or as Professor Forkner calls it, the natural numbers.
So this is the sum of the natural numbers. So I think here the kind of point is that there is like a mathematical equation, and what is it again? N times
n plus 1 over 2.
So n times the quantity n plus 1 divided by 2 is equal to the sum of all the natural numbers from 1 up to n. Okay. Yeah, we should probably, if we were actually really good, we would probably like have an equation and we would write it on the screen or something. But anyway, hopefully that makes sense. The point is that there's like a closed mathematical expression that can give you the sum of the nth number of natural numbers. Yeah. So there's like, So far we've done it with a loop. We just done it like hand cranking, and then we've done it with a loop, and then we've done it with this kind of mathematical expression. And
there you go. Yeah, so there's tons of ways of doing it. Today we're going to talk about doing it recursively, and that all starts with a method, and I'm going to call it sum and take in my n, right? We've been calling our n 5 for the past, previous solutions. So in here, I need to think about, okay, so I want this method to call itself in such a way that I can achieve a 5 plus 4 plus 3 plus 2 plus 1. So how might I do that? Well, what does every recursive method need? We start with some kind of what?
The base case.
The base case, right?
Yeah. So I think, so the idea is that you can take some problem and then reduce it to a smaller problem of the same type. until you get to a problem that's so easy that we call that the base case, right? And then the whole thing kind of unravels. Yeah. And so we have some kind of a base case. It's like the easy case is where we stop or something like that.
Yeah. So we can look back up to when we did it by hand here. I can think of it as going from 1 to 5, but I think recursively n is 5. So I should probably do, all the way down to 1. So start with 5 plus 4 plus 3 plus 2 plus 1. So technically there's another number in there. What number is that?
0.
0, right? So that would be my base case where I stop, is if n is 0, right? And then what do I want to do then? I want to return something. What do I
Wait a minute.
return?
So the base case can't be 1. If the base case is 1, you just return 1, right?
Could do that.
I think.
But it's addition, so it doesn't matter, right?
Yeah. Okay.
So I could return n, right? Or return 0. Or I could fix it a little bit. Do something like that, right? So here it's saying, okay, if n is less than 1, then we're just going to return n, right? So what's left? We have, imagine we have already solved this recursively. We have 5 plus 4 plus 3 plus 2 plus 1. Where do I want to stop? Well, plus 1 or plus 0, either way, right? I'm just going to return n, which is 1 at that point.
So the less than or equal to 1, what if what if n is negative? Then we're just going to return
it just returns the negative number.
Okay. Okay, fine. Okay. All right.
I don't is it?
Well, I mean, negative numbers aren't natural. So anyway, I think, yeah. Okay. Let's just keep going and see what happens.
Okay. Whoops. All right. So now we're on to the recursive call. And if I can get to it, here we are. So now I'm into my recursive call. I want to return something that will give me the output of this plus this, right? This 5 plus 4 plus 3 plus 2 plus 1. Or 4 plus 3 plus 2 plus 1. Or 3 plus 2 plus 1. Or 2 plus 1, right? So I can think of the rest of it as being my, what do we call it? The leap of faith, right? Where we have this recursive call to n minus 1, right? But that's not the whole thing. But what that's giving me is the rest, right? It's going to go through everything all the way down. If this was 5 plus 3 plus 1, it would be minus 2, right? But here it's minus 1 because I'm going through every single one here. But I'm not adding anything. What am I adding? Well, in each of the explanations I gave, right, we have 5 plus 4 plus 3 plus 2 plus 1. Well, this is sum of n minus 1. So that means that 5 is n, right? So if I go back here and say n plus sum of n minus 1, now we reach this 5 plus 4, and then n is now 4, and 4 plus 3, and then 3 is now n, and 3 plus 2, and then n is, going to be 1, and then we return this 1. So then it goes 2 plus 1 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15.
Yep, I love it.
So now sum of 5 should be 15. These negative numbers should just be negative, and that's this line right here where we're returning n.
Yeah, that's that part. Yeah, so I love this because, okay, so what you're doing is you're taking, so we want to find the sum of all the numbers starting kind of with 5. Okay, so that's kind of a big problem. So what we can do is that, okay, well, actually, it's really just the sum of 5 plus the sum of 4, the rest of them, right? Well, when we look at 4, well, we can say, well, that's really just 4 plus 3, 2, 1. And so then we look at that, we're like, well, the sum of 3, 2, 1, well, that's just 3 plus 2 plus 1, and then 2, and then plus 1, and then finally we get to that base case, which is just 1. It says, oh, I know the sum of 1 is just 1, so I'm going to return 1. And so it goes back to the previous call, which was 2 plus 1, that's 3, which gets returned to the previous call, etc. And the whole thing unwinds until finally we get to the original call, which was 5 plus the sum of 4. Well, all of that is unwound, and we now know what the sum of 4 is. So we just add that to 5, and bam, we got the answer.
Absolutely, yeah.
Yeah.
So if I didn't want this negative number to work, what should I return instead?
That's a good question. Let's see here. So let's say we wanted to include all of the negative. Maybe that's a more difficult question. So I don't know. It feels like the base case, since we're talking about natural numbers, those are all just the positive integers. And I think it includes 0. I guess the base case would be 0, maybe the way you originally had it. So if n is equal,
what we could do is say if n is less than 1, or if n equals 1, right? Then we'll return 1. I could n 1 interchangeable at this point, right?
Yeah.
So then beforehand, I could say that if n is less than 1, then what do I do? This means it's not natural, right?
If it's less than, I think 0 is considered a natural number. I could be wrong. I'm not sure. I can Google that, but.
Okay. Well, all right. We'll do less than or equal to 1, return n again. So then it should work for 0, right? This covers 0 through 1. This says anything less than 0. Well, I can just throw new illegal argument exception.
So I just Googled it. The natural numbers are the positive integers. So it starts with 1. So 0 is not a natural number. So I think, yeah. So our base case should be 1.
Okay. So now if I call sum, actually,
I take that back. I just looked at the Wikipedia. Some people do include the 0. So there's the non-negative integers, and then there's the positive integers. And so if you want to call the natural numbers non-negative, then 0 is technically non-negative. So anyway, yeah, it's a little detailed, this maybe not.
Okay, hold on. So we're going to loop through here, and I'm going to print out I, and then I want to print out sum, and then the sum of I. Whoops, sum of I. I'll probably make that a println. So this will go from -2 to 2. And then crash because it's not natural. So then if we do -1, crash because it's not natural. But 0 should work, right? If we go from 0, 1, 2, that should be fine. Not natural. How come?
Yeah, you have to go back up to the original code. Right here. So if n is less than or equal to 0, let me see. So
here if it's less than 0, I want to throw in a legal argument, right? Say that's not natural. Here in my base case, if n, so it's greater than or equal to 0 at this point, right? At this base case. So if n is less than or equal to 1, aka if n is between 0 and 1, return n, which is true, right?
Sure.
And then, because that's when n equals its sum. And then we can just return n. Otherwise, we can do the recursive call. So now this loop should run just fine.
Right on.
And then obviously break. If
wait a minute. So sum equals sum of I. So I'm not so so the sum of 2, okay, sum of sum 2 is 3. Okay, good, got it. All right. And so we could make the loop go up to 5, just so it's kind of clear, because we were using that 5 example quite a bit. Cool. All right. So the sum of 5 is 15. Sweet. Yeah. A couple of directions we could maybe go here. Why is this even useful? I don't know. Yeah.
Well, some languages don't even have support for looping. So you can think of functional languages, Lisp and Erlang and ML.
ML.
They don't have.
I'm not sure. I'm not sure if I'm familiar with ML.
But so yeah, you would use recursion where iteration is usually preferred. There are benefits to recursion, including its stack-like nature, which we'll talk about stacks later. But with the backtracking of recursion, we can save space complexity. And yeah.
So, and I think recursion in a programming language that doesn't have loops is actually implemented with stacks. So in a way, so anything you can do recursively, you can do with loops and stacks, because that's actually how it's implemented in the compiler. So yeah, it is, and maybe that's the disadvantage, right? Is that it involves stacks. And so you have just a limited amount of memory in the computer where you can store the state of all the previous calls. And eventually you will get a stack overflow because you just ran out of memory. So that's maybe a limitation. But yeah, I think, as you mentioned, there are certain situations where being able to remember the states of all the previous calls is a good thing, and it's a useful thing. I think Ackerman's number. I watched a computer file YouTube video. Shout out to Computer File, really awesome. Definitely check them out. But they did an Ackerman's function, and I think that's famously one of the few kind of algorithms that you can only do it recursively. Like there's not like any other kind of like a loop algorithm that you can solve it with. I think barring this thing that we just said, right, that anything you can do with a loop you can do with with recursion, and vice versa, because fundamentally in the computer it's built with stacks and loops. But yeah, it's a recursive solution. And then I think also there's just certain times when a problem just lends itself to a recursive solution, even though it might not be the most efficient or something like that. It's like just kind of the easiest to code. I love this, right? Because yeah, sure, okay, you can make a loop, or I don't know. In this case, maybe a loop is just as easy or whatever, but I don't know. Anytime you can take a problem and reduce it to the same, a smaller problem of the same type, I just like that idea. Really.
Well, the one area in Java, this is not true for every language, but in Java, recursion is pretty slow. It's intensive. So if I tried to do the sum of 100, that's quick. 1,000, that's quick. Keep adding to it. Well, there I got an overflow, I think.
Yeah.
Okay. Well, maybe sum isn't part of that. Factorial definitely is.
Yeah. Oh, and the Fibonacci and the Hanoi problems, which
Mhm.
we're going to be talking about, I think, coming up pretty soon. So that was interesting though. When you did 100 and you just kept adding zeros, it was like 500 and then 500 or something. That was kind of interesting. I didn't realize that the sum of the first 10 to the whatever, right? It's 500 500. 500 5. I didn't know that. That's kind of a cool little pattern. I never noticed that before.
Yeah. Yeah, that's pretty interesting.
So the sum of the first 10 natural numbers is bada bing 55. Wow. So you just keep adding. That's pretty cool. You just add those zeros in there. Interesting. Cool. Side note, if you add up all the natural numbers to infinity,
What about it?
yeah, it equals -1/12.
Huh.
Yeah, it's negative. It's crazy. It's crazy.
-1/12.
Yeah, yeah.
Oh, well. -1/12.
Yeah.
What for?
Man, it's something to do with the Riemann zeta function and analytic continuation. It's crazy, but it's used in mathematics and in physics, like theoretical physics, like string theory and that kind of a thing. Again, I'm going to give a shout out to, so the computer file I already talked about, but number file is kind of like the math version of the computer science one. Which is also really good. And then Mathologer is one of my other favorite YouTube channels. So I will put some links in the description. I don't know how to do that, but I'll try to figure it out. I'll put some links to a couple of these videos. But yeah, you add up all of the natural numbers to infinity and it's -1/12. And yeah, it's beyond kind of my knowledge, but these videos are really fun. So you definitely got to watch them, check them out and try to get some kind of idea about it. But basically when you're dealing with complex numbers, you have the real part and then the imaginary part, and imaginary numbers that, you know, I is the square root of -1. And so you start getting these weird things that you can start doing in the complex plane and that kind of thing. So that's kind of where this -1/12 comes up. But yeah, fun stuff. All right, is there anything else we want to talk about here about this stuff?
No, I think we've touched everything we should touch today.
Yeah. So yeah, a short one today. But yeah, we'll look forward to some more examples. And then we're gonna do some recursive backtracking and figure out what the heck that means and that kind of a thing. So all right. I think this is it. The end of another Building Janky Programs episode. Thank you all for watching.
Like and subscribe.
Like and subscribe. All right. Bye-bye.